How many of you have background in machine learning or reinforcement learning? So I'm going to give you a little bit background very fast. You're going to see this because there are multiple courses you have to take if you really have to go one at a time. So imagine I'm kind of putting everything together in a fraction of less than 2 weeks. Okay, so and about 20 lectures. That's not possible because each of those courses are a full-fledged semester level courses. So, and this is at the highest level for PhD students. So that's number one. Number two, I was just saying don't miss any labs. Okay, I hope that there is somebody to help us to run those, because the programs you could run them even if I'm not here. Okay, so make sure the most important thing is make sure you get a copy of this book. This was published in 2016. Okay, this comes with the MATLAB code, and the only thing is, as part of this course, we are offering the code. That code was basically converted to the most recent MATLAB version, which is 2023. So it should run and is pretty good. So the good thing with that is you remove the system dynamics and replace it with any system. It should work, either aerospace system or anything. You don't need the dynamics for the controller. That's the basic benefit of it. Okay, so everything is taken from this book. It's a public knowledge. There is this came out of research, and you see that there is a second author was the guy who did this. He's a former PhD student. Typically that's what happens, and they become a faculty, right, like you guys. So he's a faculty in US right now, and so this was published in 2016. So get a copy. This is very important what goes on. Okay, so with that short intro, and I'm here, so if you have questions or something, you guys can ask me. So I was also telling a few people here, if there are PhD interested students to pursue in the US, please let me know. I think there will be an email I'm going to show you. Okay, so this network control systems is a specific topic, okay, of what we call cyber physical systems. How many of you have heard of cyber physical systems? Yeah, so the cyber physical systems, the word has been coined in 2006. 2006 is what it is. So every system that you see currently being operated, we call that as cyber physical. So the reason it's called cyber physical is because you have a physical system like a batch reactor or a plane or some kind of a gear system, a battery system. That's a physical system. Then you have some sort of a controller, or what we call is a embedded processor. So you have a cyber, you have a physical system. It's basically called cyber physical system. Okay, so you can see that I have given my information here, and then there's an email at the bottom. You can email me. As I said, normally I'm looking for students with some who are interested for PhD. Okay, so this is the intro that we're going to talk about it. So imagine a world. Okay, this is what is going to happen, right? So this is taken from National Science Foundation by David Corman, and you can see that you have a building we call earthquake proof building. It's a smart building. Okay, and a smart building means it can withstand. They're using smart materials. Imagine that the wall, if the wall is going to break down, it should inform you just like a human being. There are symptoms, it communicates. Okay, that's the goal of it. Okay, so smart building is something, it is really smart. Like a human, it tells you I'm having fever, like a baby kind of a thing. And then you have the smart cars. Okay, and you have the energy efficient power grid, which we call smart grids. Okay, and so you can see that there are intelligent water resources, even a person with a pacemaker, a smart pacemaker, which for a heart. So imagine that this is where the future is heading actually. Okay, so in order to get that, this whole thing, each of these systems, we call them as smart cyber physical systems. So cyber physical systems, the word cyber physical systems were been coined in 2007, and I'm going to tell you a little bit about that. Okay, so what is a cyber physical system? So cyber physical system integrates computing, communication, and storage capabilities with monitoring and control. Okay, so CPS transforms how we interact with the physical world. So what does it mean? So let me skip this slide. Okay, so here is what is a cyber physical system. So you have a cyber component here on the left hand side, and you have a physical system, and each of these, this connection can have a wireless network, can be a wired network, or a physical connection. It could be either of them. Okay, so this is what a very a dumb man's explanation. So embedded, it's different than embedded computer systems. So all these examples like connected vehicles, you have the smart grid, you know, so any transportation networks, all these are connected, you know, they call cyber physical systems. Okay, so so what is characteristics? Cyber is integrated pretty much in every physical component. All right, and the most important thing is they operate at multiple time scales, spatial and temporal. So the question is, you have two loops in like a control. You have two loops. One loop is sampled at milliseconds, let's say. The other one is sampled at once an hour. So that is the time difference, you know, between the outer loop and the inner loop. So that's what we call spatial. Okay, and there are multiple temporal and spatial. Spatial means basically, I don't know how many of you know partial differential equations. Most of you have studied ODE. ODE is very common. We all like ODEs. But PDEs are more harder. Now, what is the difference between a PDE and an ODE? What is the difference? I'm positive you guys have studied even in undergraduate. And what is the difference between a PDE and an ODE? You know what ODE and what the word ODE and PDE? What does it stand for? Partial differential equation. So what is the difference? So one is with respect to time. PDE is also with respect to time, but it's also with respect to space, either x, like the distance. So if you look at the heat conduction, and that is basically with respect to the x, y, and z, for example. So spatial is each x, y, and z. X is varying with respect to time, y is varying with respect to time, and so that's where it becomes partial differential. Each of them you take a partial. So spatial, it can also vary with respect to space. This is where I said you got to have the map background. Remember that. Okay, and the other thing is operations that you do, it has to be dynamically reconfiguring. That means it has to organize itself and all that. That's a cyber system, and the operation has to be dependable. Somebody said you know, he does something for control for aerospace systems. Imagine if those systems are not reliable or dependable, you can't fly on a plane. So secure, that's important if you are a you know, computer scientist, but it's also important for a control person also. And then the other thing is safety. So a lot of times we want these systems to be safe. So that's also very important. So cyber and physical components are tightly integrated. They have to be connected together. If you remember, I showed you. So here you can see that left hand side has to be connected to the right hand side. The mouse doesn't work here. So I think the left and right, this and this one has to be connected properly, and it has to be integrated. Okay, so that's mainly what it is. Okay, so little history here. So if you look at it, let me see if I can remove this off. I'm not able to remove this off. Yeah, I don't know. So So this is from real-time systems to hybrid systems. That's the title. And you can see that 1949, the computers are basically, computations and in 1949. In 1973, there is the topic of real-time computations. And hybrid systems came in 1990. Hybrid means both continuous and discrete mathematics, because computers work in discrete domain, and physical systems operate in continuous domain. That's why we usually use them to we describe the behavior of a continuous system, any process, by ODEs or PDEs. And then you can see that around 2000 here, around 2000, you see that there are people that they coined the word what we call cyber physical systems. Okay. So from communication, acting, and control, I think this guy is blocking the title. I don't know. You may want to remove that little thing in there. Can you remove that out? Otherwise, they can't see the title in there. So the communications and control perspective, you'll see that people, that'd be good. I don't know why it is popping up. It shouldn't pop up there. Or you move that, if you can move it outside. Yeah, just move it to the. I think if you have a mouse, that'd be good, because you can project out on there. Yeah, go ahead to the full form. Let's go to the full screen. Yeah, the mouse is good if you have it, because then I can point out. Sometimes, it's not there, but that's okay. So I think you can see the. So this around 2006, this is how it kind from real-time systems to hybrid systems. So from communications and sensing and acting, and you can see that there is this communication side here. Yeah, if you have a mouse, that'd be good. I think because. Yeah, let's see. It makes it easier. That's good enough. So you can see here. So here you can see the communication control, and it becomes what we call networked embedded systems. So this is how the cyber physical systems came in. The word actually came in from different domains. Okay. So and if you look at control, if you are a control person. Okay, so you see that the first level of control is basically analog control. Then the second generation of control in 1980s is called digital control. And then now we have what we call is there are some network protocols, networks being inserted in the control loop. That's why we call that as a network control systems. Okay, and the minute you have a network has a protocol. So if you guys email, right? Remember when you send email, what protocol does the network uses? Huh? No, HTTP is the web thing. Huh? TCP/IP. the transport control protocol. So, and we won't have time, but there is in the book that it talks about how to bring that stuff in there. So basically you have a protocol, and that protocol has packet losses. Those packets go like in packages, kind of a thing, like you are sending so your message is broken down into different packets, and those packets go through the network, so it's discrete. And so whenever there is a packet, things get dropped. So there is delays, and there's also quantization. You have to limit the number of digits. Okay, so this is basically led into what we call event trigger, event plus time based. So this is the third generation. The network control systems is the third generation or the fourth generation of control. Okay, so if you need to do the cyber physical systems, you need all these background. It's an interdisciplinary field of computer science, control, communications, software engineering, and networking. So if you look at it, there are different degree programs in the US, and those degree programs, they offer like a certificate or course on cyber physical systems. So it's unlike the electrical engineering or computer engineering, you have to have the cyber physical systems. Okay, so cyber physical systems are deeply integrated. Look at that. There is a transportation. Okay, there is this transportation field, energy, industrial automation, healthcare, and critical infrastructure. So they all can be called as cyber physical systems. That's where in the future. That is the future. So you can't have these silo degrees like electrical and all that. What industries are looking at is basically having somebody in control, communication, software engineering. That's what is needed as future job opportunities. So one of the examples is make cities smarter. They call smarter cities. Even in India, Modi and other prime ministers, they talked about smart cities, right? You might have heard that. So basically smart cities, you have parking, and you don't really use an app, and basically it tells you when you are in that area where is your place to park, and you go there and you park it. So you don't pay, automatically deducted from your bank account. So many stuff going on. So you have the PEVs. So everything this is kind of a smart city. Smart grid. Now imagine you have a wireless area, wide area network connected with a server, and you have the smarts, all the different generators, smart home. So the idea in a smart is able to heal itself if things break down. It motivates customers to participate. It resists attacks, people trying to attack. It accommodates all generation options. So if you are a power person, you should be able to accommodate renewables like wind, solar, okay, and the traditional diesel engines, and it's able to run efficiently. So a smart grid delivers electricity from suppliers to consumers using two-way digital technology to control appliances. So you can see that it's a big deal. Okay, so in the future, the industries are going to look at not electrical engineer. An electrical engineer who has taken a course on compilers and software programming, who also knows how to do, networking. So imagine that. That's what is expected as a future engineer, not like the electrical old curriculum we have studied. And those things will go away in a matter of time now. Okay. So this is a picture of a smart grid again, and you see that it's envisioned that the smart grid essentially will likely have a control system that analyzes the performance using distributed reinforcement learning, and we're going to talk about that. The whole course will talk about it. So network enabled manufacturing. So this is the projects with Boeing that I have been involved, and my network manufacturing, everything, all the tools, everything is connected through a wireless network. So whatever I'm doing, it automatically records the information. Okay, and they have RFID tags. How many of you heard of RFID tags? How many of you heard of RFID? Yeah, what is an RFID tag? Okay, let me help you. The RFID stands for radio identification detection, right? RFID, radio frequency identification. So it's a little chip with a wireless connectivity. It looks like a piece of paper with a little digital circuitry on it, okay? And you put it on anywhere, and it will tell you what the name is. So what we call that as a cradle to grave. So it starts when something is born, a product is just born, and you monitor the life of that, and it's stored on that. There's a little memory. It's called a mobile database. Okay, it's a mobile database, and it goes with the part until the part breaks down. And the thing is, it saves like a human. Imagine you have a patch. I don't know, some of you know that in medical area also. And that patch is saving all the life, like the heartbeat, everything of us on that patch, so that anybody can, if somebody faints and dies, Abdul Kalam fell down one time, right? And so if anybody has any health problems, you can actually read so that somebody else can treat it without having somebody carrying all that paperwork. Okay, so it's an RFID tag, is widely used in aerospace industry. So we were doing this in 2000, and we can also look at real-time systems. So most of you know real-time location systems, GPS, right? And what is the problem with GPS? Huh? One is accuracy, but does GPS work indoors? Huh? No, it doesn't work indoors. It's not good in indoor environment. So real-time location systems are mainly systems that are like GPS. What will happen indoors? Indoor environments. Let's say you have a mobile robot and you want to track a path. So they have used all kinds of other things, technology like IMUs. Have you heard of IMU? Inertial units, right? They use that with some dead reckoning. And so the main reason is because you cannot position. You don't know accurately what is the location of that. So basically, we are looking at in 2000 things that you can locate indoor environment because GPS is unavailable. Even outdoors, some places you won't get GPS. Okay? So there are a lot of opportunities for cyber physical systems. Pretty much everything is a cyber physical. Self-organizing factories. This is what is going on in the future. Embedded intelligence. I usually play a video of this future. Unfortunately, I don't know whether I have a network connectivity, so I didn't play the video. There should be a video. There are a lot of videos on my website. So there is a video that maybe we have time, I can bring my laptop and we'll do that at the end of the course, And embedded intelligence. So this is another important. So there is the RFID tag with AI going in each of those tags. This is embedded as part of the physical system. So basically you are proliferating all these physical systems with these embedded with some machine learning component in there. That's what is happening in the future. So if you are an engineer and you want to be successful, you can take courses just in electrical engineering. And as I said, you have to have the background in software engineering and other things. That's how it's going to be in the future. Otherwise, you will be outdated pretty fast. You'll be outdated. This is what is happening. Okay? So smart systems, from sensing, computation, and control, they're all integrated into one another. Okay? So we call that as informatics or smart healthcare. So this is what is happening even in India, for instance. And that's the future, what's going to happen in the future, okay? Smart environments. So, for example, I can control my home temperature from here in India. I have an app. I can even open and close the doors of my home. I can control it from here. If I have a network connectivity, if somebody is waiting to get in, I can actually open the door. And my home is captured with cameras, okay? There is a monitoring. I can turn it on. If somebody is a maid or somebody is coming in and she comes to clean, I think it monitors. So I can do it even I'm in India, for example. So those kind of systems are currently exist. And this is not too far that you're going to see at homes. And in the smart homes, you see that there is a solar on the roof. It basically provides electricity not only for the home, and it basically sends the electricity to the grid. So you can actually sell the power to the grid and you get paid. And in the night time, you can use the electricity you buy from them. So there are a lot of things are going on. And it's not too far that you're going to see these things in real life. Okay? So keep that in mind. So then cyber infrastructure. Already Vande Bharat Express. So you can imagine now there will be a lot of automation going on, right? To prevent two trains colliding. A lot of stuff. Bridges. You remember already you have those fast tags, right? You remember that's an RFID tag. Like in the track goes, you pay automatically, they deduct from. So those are RFID tags. You have it on the car and it reads as you come closer. So there are a lot of things that are getting automated. So remember, guys, it's not too far. If you are young than me, okay, I'm telling you right now, 20 years past. I haven't told you what is going to happen. So if you're a double E, within 10-15 years you will get outdated unless you update yourself. That's what is happening. So as an electrical engineer, you got to have software background. You also have to have some courses in computer science, some courses in mathematics. I think we were already talking about it. Okay? And Internet of Technologies are going to play a significant role. IoT basically brings in the idea of a sensor with some sort of a network. Very small, you can measure a lot of different things, okay? And they are placing these in appliances, vehicles, buildings, cameras, pretty much everything. So cyber physical systems, there are degree programs. New degree programs are being offered, just like electrical. And the funding agency in US, they changed the name to cyber. It used to be electrical and physical communication systems. They changed the name to cyber communication and control systems. So the names have been changed now. So you remember electrical department in US is called electrical and computer engineering. Now it's being changed to cyber. A new set of courses. So remember how many with AI coming in, people are getting laid off? Both software engine, that's what is going to happen, guys. If you are young, take courses now. Okay? So you ask me my background. My bachelor's is in electrical engineering. Master's is in computer science. And PhD is in robotics, which has the blend of computer science. So I was one of the very early ones who was studying, learning AI. I took so many courses. During that time, people never heard of that in the 80s. Yeah. And you see that Google and all these companies laying off. It's going to happen. India will be affected. India is in a good place because a lot of young people. And most of you, if you are interested to learn, this is the way to go. Yeah. All right. So new set of courses. So, but there are a lot of opportunities. If you have an open mind, there are a lot of smart healthcare. So there are a lot of opportunities in healthcare. So opportunities are abundant, provided you have improve your skill set. Emergency response, security field, and so forth. So why is that a lot of opportunities? How many of you heard of big data? This is a very new term, big data, a few years ago. So what generates data? How much? Complex systems, smart environments, fleet of vehicles, process control, smart grid, they generate data. How much data? So if you look at the data that these things generate, Boeing jumbo jet, when it crosses from, so like the flight I took from US to Europe, it generates about 650 terabytes of data. Terabytes of data. The human activity generates about 1 gigabyte of data. So imagine you are accumulating the data, it becomes big data. So one sensor generates about 2 megabytes. So all these things coming in as part of cyber physical systems. So what makes big data, Microsoft defines big data is basically is a process of applying serious computing power. Massive and highly complex sets of data, okay? Data in rest, data in motion, data in many forms, and data in dot. So there's a lot of needs for cyber physical systems, new calculus. So when we talk about cyber physical, that means you're talking about new fundamental science like ODE and PDEs. Okay, dynamics at different time scales. There are delays. These delays are random because the network that you're operating a computer or a communication network, basically that's modeled as a stochastic system. Most physical systems are modeled deterministic. So there's a difference between a deterministic system and a stochastic system. What's the difference? What's the difference? I know many of you are master degree students, and all these things we studied in undergraduate, right? We studied this in undergraduate, but what is the difference? So there is some variability. So it won't show the same behavior every time you start, right? So there will be some variability, very fundamental, very basic. So the process variables vary with respect to, it is basically varying in a distribution. In a deterministic, you don't have just one spike. In a stochastic, it has some sort of a distribution, so it's varying with respect. It has a mean value, it has some variance. Okay, so all the process, like the computer networks, the wireless networks, they are defining them as random variables. Okay, so you'll see that when you run the code in the labs, you'll see that you won't get exactly identified results, because when you're running it next time, you're initializing it, and so when you initialize it, there will be a random seed, and that initializes at different values. So this is very important. Okay, so the delays and packet losses. So usually in that network, you have some delay, and those delays are random. They are not deterministic. You can't say every day, let's say you're going from your hostel block to, or from your home to your campus, you can't exactly say it takes 15 minutes. You know, one day it may take 15, one day it may take 1 hour, some days you may take half a day if there is a accident, and some days, you know, you will take 10 minutes plus few seconds. That's the variation you're talking about. So any time when you have a continuous system and a discrete, we call that as a hybrid system. Okay, the time is not global, because each system has its own time, and time is local in this case. So you have to have a software and hardware co-design tools. So this is why I told you, even if you're a EE student, and remember, I am actually at the end of my, maybe another 10 years I can work. So if I would have been in India, all my friends are already retired. So I'm considering myself as a super citizen, right? 58 is the retirement age. 60, maybe if you work in IITs, they go up to 65. Okay, but remember, in US there's no age. You can work for 95. So and people are, a lot of faculty that I know of, they're already like 78, 80. I have a faculty member, one well-known guy in Yale University. He said he's 92. He's going to have a birthday. He called me and said, let's have a symposium on adaptive control. He's a well-known guy in adaptive control. So 92 he is. So what I mean is, I don't know whether I'll survive at that age, but remember, if you're really young, you really have to have all these skills, otherwise you will be out in 5 years. I don't know whether you know, recently, what is that, Narayan Murthy, I think in that Infosys, they fired a few people, they are not keeping up, and I'm telling you, this is true. I've seen about a large quantity of Indian students coming out to a lot of colleges, don't have the skill to survive. Let me be blunt on that. Yeah. There's one thing to study a course, get a grade. I don't know, here you gives in A, B, C, D, or do you give them in percentage? Grade is there, okay. Grading system. So you can get a grade, but that person doesn't know what ODE is. So I did my undergraduate in 80s. I still remember all those differential equations. I can actually solve those differential equations. Yeah, you should be like that. So there are a lot of things you study, but you need to know how to do it. That's important. The skill is very important. Okay? So I think that's the software and hardware. That's a pretty common thing. You got to have it nowadays. It's given. It goes without, there's a word called goes without saying. You got to have that. Otherwise you will not survive. Okay? So there's also issues now when you bring in computers. There's also an issue of security and privacy stuff, right? All that also is different from a cyber physical system, because these are real-time systems. They're running in real time. Even computer science people cannot handle this. You can't use some of those. So that's why you have to have a separate degree programs in these systems, okay? I'll quickly going through. So security and privacy, these are not legacy systems. So you can see that they have to come up with different new stuff, and this is a real-time system. So if somebody putting an attack on a computer network, in a worst case, if the computer hangs up, what do you guys do? When computer hangs up, what do you do? You switch it off. But you can do that same thing with a lot of real-time systems. You can't just go and bluntly go and turn it off. Things go out of really, like in a car. Imagine you turn, suddenly you're driving at 50 miles an hour and you can't turn the car off. So there are a lot of things like that you can do if it is a cyber physical systems. So even a computer science people, you have to have skills. So they are studying in real-time systems. They talk like an undergraduate student, and I keep telling them all this is done in 80s. So you have to have they have to learn also skills. Okay. So now a network control system. So what is a network control system? So network control system is a small subset of cyber physical systems. So you can see that here you have a controller. In the traditional world you have a physical system. These two are physically connected with a hardware wire. Now you see that on the left hand side you have different physical systems, the controllers, and they're all connected through a wireless or you have a wired. So a good example of a wired network is a automotive vehicle. All automotive vehicles has a bus, CAN bus. It's called controller area network bus. And that bus is basically IEEE. It's a standard in there. And it uses some sort of a protocol. Okay. So what is a protocol? Protocol is a way of communicating. So let's say we all are here. Imagine when all of us talk at the same time, what will happen? What will happen? If all of you talk at the same time, what will happen? Nobody will understand anything. The same idea. So if you have a cable, if all the subsystems are communicating at the same time, they all collide, nobody gets the information. So the protocol is a way of exchanging information in a systematic manner, and it has a performance so that you want to keep that bus operating